everyone, this is EddieDoesMath. Welcome to my channel. I have a gift for you. Click the link in the description below to get practice problems on circles on the SAT. Now it's time to lock in. I'm about to cover everything you need to know about circles on the SAT. Let's start with the basics, circumference and area. Let's write the circumference and area of a circle in terms of its radius or diameter. So we have our diameter is d, and we know that our circumference is always going to be pi times the measure of the diameter. So pi is approximately 3.14. If we take that yellow diameter and place it around the blue parts of the circle, around the edge of the circle, we will need a little bit more than 3 of those diameters, exactly pi number of diameters, to get the circumference of the circle. Now, d is also known as twice the radius. So that's where we get 2 pi r from, because twice the radius is d. Now for the area of a circle, we know this as pi r squared, and that's because whenever we have r squared, which is the area of this box, if we were to build a little radius here, a little radius here, and we build this box, the area of this box times 3, a little bit over 3, exactly pi, would give us the area of this entire circle. Now let's take a look at some problems. The circumference of a circle is 14 pi. That means that 2 pi r will equal 14 pi. Meaning 2r is equal to 14 and r is therefore equal to 7. Our radius is equal to 7. Given this information, we can find the area of the circle being pi r squared. So we plug in 7 into the r. We're left with 49 pi. Similar question comes next. The area of a semicircle is 32 pi. A semicircle is half of a circle. So if the area of a semicircle is 32 pi, then half of pi r squared will equal 32 pi. This is because we're working with a semicircle. So multiply both sides by 2, cancel out the pi's, we get 64 and r squared, so the length of our radius will be 8. Now in order to find the circumference is 2 pi r, and we can plug in 8 for the r, leaving us with 16 pi. These are some ways that circumference and area can come out on the SAT. Now, find the shaded area in gray in the following shape. This 4 feet is a distractor. We actually do not need it at all. All we need is this first circle and subtract the second circle, and we'll be able to find the shaded region. So the area of the first circle minus the area of the second circle is what we're looking for. The area of the first circle will be pi 12 squared minus the area of the second circle, pi 10 squared. Now we got 12 because 10 plus 2 is 12. So this radius right here going out to the first circle, the bigger circle, will be 12 feet. Once we have this, we'll have 144 pi minus 100 pi, and we're simply left with 44 pi. Don't forget your units of measure. This will be feet squared since we're talking about area. A beautiful problem, nonetheless. It shows up a lot on the SAT. Circle inscribed in a square. Let's check this out. I want to find the shaded area here. So I'm going to take the area of the box, the square, and subtract the area of the circle. Now my radius is 10, meaning my diameter will be 20, giving us one side of that square. So the area of the square will be 20 squared minus the area of the circle will give us pi 10 squared. And if we solve this, we will get the area of the shaded region. Excuse me, I'm a little bit sick. 20 squared will give us 400 minus 10 squared is 100 times the pi gives us 100 pi. And all that will be in inches squared, just like that. Now, what percent of the rectangle is not shaded? Seems like a harmless problem, but once we start diving in, there are some little things that we have to pay attention to in order to get this fully correct. So what percent of the rectangle is not shaded? So we'll be finding the area of the circle. Then we're going to put it over the area of the box, right? As long as we can find the area of the circle, that's the only area that's not shaded. I'll put it over the area of the box. So the area of the circle is pi r squared. The area of the box, how do we find that? Well, the radius is 2, meaning the diameter is 4, and that gives us the height of this box. But be careful here. The catch is that 84 is in inches, not in feet. We must work with the same units of measure. So 84 divided by 12 is actually 7. So we have 7 feet. So we have 7 times 4 is 28. So we have 4 over 28, which is 7, or 1 over 7. So we have pi over 7, and we can plug this into our calculator to get pi divided by 7. We can do it on the side here, and we'll get some percentage. Let's do it really quick on the side here. Pi divided by 7 gives us approximately 45%. So we get 0.4488, and depending on what the question asks you for, usually it's to the nearest tenth or to the nearest whole percent. I would say 45% would be a sufficient answer here. All right, on to arc lengths and sectors. An arc length will be this highlighted portion right here. This will be our arc length right here. And the area of a sector would be all this shaded. Okay, so that's the difference between arc length and a sector. In order to find the arc length of a sector, think about what that means. We're looking for this small length, and it's definitely a piece of a larger circle. Now we know how to find the circumference of a circle, and we're given the degree measure of this sector. So 40 degrees. What percent of the entire circle is this little arc? Well, we know it's 40 degrees of how many degrees in a circle? 360. So that's the percentage. That's the portion of, that's the section of this circle that we're talking about. So times the circumference will give us our arc length. And if we take 40 degrees over 360 degrees times our area, that will give us the area of the sector. Now, circumference and area are relative to the entire circle. So the circumference of the entire circle will be 20 pi, because 2 pi r. So we have 40 over 360, that's 1 over 9, times 20 pi, and that gives us 20 pi over 9 centimeters. Now over here, with our area, we'll have 1/9 times pi r squared. So that'll give us 100 pi. So 100 pi over 9 centimeters squared. Same idea for this second example. We'll have 120 degrees over 360 times the circumference, which is 10 pi. And 120 over 360 is a third, so we have 10 pi over 3 centimeters for this arc length. For the area, I would have a third times pi r squared, so 25 pi. And so 25 pi over 3 centimeters squared will be the area of this sector. So you have the area, and we have the arc length. Now let's put little patterns to this, right? The pattern to the arc length, about whatever theta is, we put it over 360 and we multiply by the circumference, C for circumference. For the area of the sector, we would take theta, put it over 360, and multiply by the area of the circle. So keep it simple. There are a bunch of formulas that you could memorize, but if you truly understand where this is coming from, this is definitely the way to go. So let's try some practice problems. The area of the two sectors in the diagram is 72 pi square feet. So the area of these sectors, this one and this one right here, added together will give us 72 pi square feet. Now we're given this right angle, meaning that all of these are right angles. So what we actually have here is a semicircle. So half the area of the entire circle will be equal to 72 pi. The pi's cancel, multiply both sides by 2. R is equal to 12. So what we just found is that this is 12 feet, and all these are radii. So they're all 12 feet. So if you want to find the perimeter of this figure, I'm going to do 4 times 12, since I have each of these right here. And then I need to find the arc lengths, 1 and 2. This make up a semicircle, so half of the circle that we have. So plus 1/2 times the circumference, and the R will be 12. So we have 48 plus 12 times, well, these cancel. So we have 12 pi, and that's our perimeter of this figure in feet. The diagram shows a sector of a circle. It looks like all of this is 270 degrees since this is 90 degrees right here. The radius is 10 centimeters. Work out the perimeter of this shape. So let's first look for the arc length. The arc length will be the degree measure that we're given divided by 360 times the circumference. The circumference is 2 pi r, just like this. So 270, 360, that's 3 over 4. 2 cancels out with this 4, and 10 cancels out with this 2, leaving us with 5 times 3 times pi, which is 15 pi. Now, we must add these two side lengths as well, and they're both 10 centimeters. So our final answer, perimeter, will be 20 plus 15 pi, and this is all in centimeters. This shape is made from two identical sectors right here. So we know this is 8 centimeters. If this value is 3, then we know this is 5 and this is 5. Great. Now all we need to know to find the perimeter of this shape is to find these arc lengths. How do you find them? Well, 120 divided by 360, that's the portion, that's the section of the circle that I want, times the circumference. Well, circumference is 2 pi r. 120 divided by 360 is a third. So here we have 16 pi over 3 for just one of these. Well, we have two sectors here, so the perimeter will work out to be 2 times 16 pi over 3 plus 5 twice and 8 twice as well. If we add these all up, 16 plus 10 is 26 plus 32 pi over 3, and all this will be in centimeters, and there's our perimeter. This is how we combine different concepts, and that the SAT loves to do that. Next question. The figure below is made from two sectors of circles. Okay, center O. Find the perimeter of the region labeled R. So if you take a look at this, we have a larger circle, and we're going to be subtracting a smaller circle to get R. Now we want the perimeter of this region, not the area. So the perimeter, we know that this length right here is 4. So right off the bat, we know our perimeter will be 2 times 4 plus these two arc lengths. Let's do this in different colors here. I'm going to call this one green. And I know that the radius of this part of the sector, this green pizza here, will be 8, because 8 plus 4 is 12. Given this, I can find this arc length by going 60 degrees over 360 times the circumference with radius r. So 2 pi times 8. This is 1/6. 2's cancel out, and we're left with 8 pi over 3. Now let's figure out this outer arc right here. That radius is 12, and we'll use the same pattern. 60 degrees divided by 360 times 2 pi, radius of 12. So this is still 1/6, and guess what? 6 goes into 12 twice, so 2 times 2 pi is 4 pi. So if we add these up here, I'll have plus 8 pi over 3 plus 4 pi, but I'm going to rewrite that as 12 pi over 3 so I can combine like terms. So I have 8 plus 20 pi over 3, and all this is in centimeters. So I hope this helped you understand circumference, arc length, area, and sectors a little better. Last one here. The arc length of this sector is 70 over 9 pi. The arc length is 70 over 9 pi. So this right here, from here to here, is 70 over 9 pi. Now, I don't know what this degree measure is, but I do know that whatever it is, over 360 times the circumference, 2 pi radius of 10, will equal 70 over 9 pi. Now, notice, pi's will cancel out from either side. I can divide both sides by 20. So I have theta over 360 degrees is equal to 70 over 9 times 1 over 20. These cancel, so I get 7 over 18. Now, in order to get theta, I can multiply both sides by 360, and this is where we start to smile because we notice 18 is a factor of 360. So I get 7 times 20, which is 140 degrees. Now, why is this information important? Well, it's crucial in determining the area of this sector. The area of this sector will be 140 divided by 360 times the area of the entire circle, which is pi r squared. Now, 140 and 360 both have a 10 in common, so we can cancel that out. They're also both divisible by 2. 10 squared is 100, and 100 is divisible by 2, so is 18. So now we have 7 times 50, which is 350. Don't forget the pi, all over 9, and centimeters squared would be the area of the sector which we wanted. Let's go over some circle theorems involving right angles and some general angles as well. First, some reminders of useful shape properties. Angles in a quadrilateral add up to 360. So all these angles here, 1, 2, 3, 4, will add up to 360. The base angles of an isosceles triangle are equal, right? These angles are congruent because the opposing sides are congruent. Now, let's get into some circle theorems that apply to any angles and lengths when circles are involved. Here we see T, a tangent line, and here we see R, the radius. The tangent meets the radius always at a right angle, always. Every tangent line to a circle will make a 90-degree angle with the radius of that circle. Number 2, angles in a semicircle are always 90 degrees. This angle is 90 degrees. If I drew any triangle where the point, right, the angle is touching the circumference of the circle, then that angle will be a right angle every single time. And this will be very useful in solving problems. Number 3, angle at the center is twice the angle at the circumference. So this kind of goes back to rule number 2. If you think about it, a straight line is equal to 180 degrees. And if we created 2 lines like this, 90 is half of 180, and this works for any inscribed angle. So angle at the center, boom, right here, this angle right here will always be twice the angle at the circumference. And number 4, this one is super, super useful as well. Angles in the same segment are equal. X and X are equal, and Y are equal, and that will be very useful. Number 3 does have some special cases. If we have 2x, the reason that we have 2x here and an x is because notice how this is a radius and this is also a radius. So it's actually an isosceles triangle. So this is also x. And reminder, for a triangle, the 2 non-adjacent angles summed up equals the exterior angle. So this is where that shows up again. X plus x is equal to 2x. And furthermore, if we have 2x here and let's say some other angle here, this will still be 2 times this angle, just like we had up here, even if it's an obtuse angle like this. Or we call this an angle bigger than 180 here. All right, let's try some problems. So solve for the missing angle. We know that since AC goes through the center of the circle, this is a right angle. So if that's a right angle, we've got a 30, 60, 90 triangle on our hands. Here, we want to figure out the angle x. We know that the radius creates a right angle with any tangent line. So if this is 51 degrees, the remaining portion will be 39 degrees because those add up to 90 degrees. I also know that an angle at the circumference will be half the size of the angle at the center. So 120 divided by 2 is 60 degrees. I also know that a circle contains 360 degrees, and subtract that 120, this angle right here will be 240 degrees. So if I were to add all these up, I know a quadrilateral adds up to 360 degrees. So I could go 39 plus 60 plus 240 plus x will be equal to 360 degrees. Let's go ahead and sum these up. X will be 360 minus 339, and we should get 21 degrees for our value of the missing angle x. Now, equation of a circle. This is kind of the pinnacle, the summit of what we need to know about circles. And this is where it can get a little more algebraically complex, but stick with me here. Let's check this out. What makes a circle special is that every point on the circumference is equidistant from the center point. So let's derive the equations of a circle with center point 0, 0 and a comma b. We'll be creating a general equation for a circle right here. But first, let's check out this circle with center 0, 0. Imagine if we have this 0, 0 and we wanted some radius r. Let's call this point x comma 1, x comma 2. Then, using our Pythagorean theorem, I can say this is x comma 1. Ooh, that should be y comma 1. Right here, x comma 1, comma y comma 1, y sub 1. So x sub 1 and y sub 1, let's find the Pythagorean theorem here. The Pythagorean theorem would be then x sub 1 squared plus y sub 1 squared is equal to r squared. But if I wanted to do this with any point around the circle, how would I get this? Well, we would have to find the difference between the x value and this 0, comma 0. But that's always going to be x squared plus y squared equals r squared. So, let's see if the center is not at 0. If the center is not at 0, then that would mean we have transformed. We've horizontally shifted a to the right and b upwards. So that must mean we can subtract a from x from our transformation of functions that we know, subtract b from y, and this will still equal the radius squared. And that's what takes us to the equation of a circle centered at h comma k. We'll have x minus h squared plus y minus k squared will equal r squared, and this is the general equation of a circle that will always hold. So let's check this one out. Write down an equation of a circle with a given center and radius in each case. If the center is 0, 0 and the radius is 3, just like we saw in our previous example right over here, we can say this will be x minus 0 squared plus y minus 0 squared is equal to 3 squared. And I'll simplify this in a little bit, but I want to show you the pattern here. Check out this pattern that we have for each of these. And for letter C, I'll have x minus a negative 6 plus y minus a 10 equal 4 radical 2 squared. They all have the same exact structure. Now, once we simplify, we can get x squared plus y squared is equal to 9. Here, we can leave it the same. Here, we can do a little bit of simplifying. And 4 radical 2 squared gives us 32. Boom. Now, given the equation, write down the coordinates of the center and the radius. For letter A, we have 0, comma 0. And our radius is not 49. Careful. Reminder. The right side of the equality will always be r squared. So think about what number squared gives us that 49. That number is 7. Letter B, the center of our circle is negative 3, comma 2. Keep in mind, our general equation of the circle always has x minus k and y minus x minus h and y minus k. That's where hk, the center, comes from. And our r will be 9. 9. Let me rewrite that. 9. Boom. Letter C, we have a center at negative 7, comma 0, and our radius will be not 18, but the square root of 18, and that can be simplified to 3 radical 2. Now let's try some more difficult ones. Equations of circles in expanded form, and this is all we have left for today. Let's lock in. Find the coordinates of the center and radius of each of the following circles. So in order to do this, this takes us way back to quadratics and completing the square. In order to complete the square, we need all the variable terms to be together and grouped together first. So we have x squared plus 4x. We have y squared minus 10y. I'm going to move this constant of negative 7 to the other side. Now, what more do we have to do here? We can start completing the square. Take half of the coefficient of x and square it. Take half of the coefficient of y and square it. But while we do this, don't forget, we must do those things that we just applied on the left side of the equality to the right side of the equality as well. So now we have x plus 2 squared plus y minus 5 squared is equal to, this is 25 plus 4 plus 7, that's 36. So what's the center of this circle? Nice, -2, 5, and what's the radius? Remember, not 36. It's the square root of that constant on the right. Let's do one last problem together. Here we go. 12x squared plus 60x, and we have plus a 12y squared minus 84y, and we have -75 or +75 on the right since we've added this -75 to both sides. From this, the first thing we have to do is not take half, but factor out the leading coefficient. Factor out the leading coefficient to get 5x here, and then we'll add 5 halves squared, plus factor out a 12 here as well. This will be y squared minus 7y plus a -7 halves squared is equal to 75. Now here we have to be careful. Completing the square, we must add a 12 times 5 over 2 squared and add a 12 times -7 over 2 squared. Now we have 12 times x plus 5 over 2 squared plus 12 times y minus 7 over 2 squared equals, let's see what we get here. On the bottom, we're going to have 2 squared, which is 4. It'll cancel out with this 12 to become a 3, right? Keep in mind 2 squared is 4. So same thing happens here. This will become a 3. 5 squared is 25 times 3 is 75 plus another 75. These two give us 150. This right here, 49 times 3 is 147, I believe. Let me check really quick. 49 times 3. Yep. And we add these together, we get 297. All right. Well, then I'm not used to having these 12s out in front, so I'm going to divide everything by a 12. Everything. The entire equation. So I get x plus 5 halves squared plus y minus 7 halves squared is equal to 297 divided by 12. Now I know that both of these are divisible by 3, so I can rewrite this as 99 over 4, and I don't think that's divisible anymore, so we'll leave it just like that. So what's our center? The center of this circle will be -5 halves, 7 halves, and my radius will be the square root of 99 over 4. Now we can take the square root of 4, that's 2. The square root of 99 will give us the square root of 9 times 11. So that gives me 3 radical 11. And there you have it. If you found this useful or learned something new, make sure to like and subscribe. By the way, don't forget the link in the description below will get you access to all the problems we covered today. Let me know down in the comments if you'd like to see anything in particular in preparation for the SAT. And I'll see you again soon.